In the Bohr model of the hydrogen atom, we have one proton in the nucleus, so I draw on a positive charge here, and a negatively charged electron orbiting the nucleus, so kind of like the planets orbiting the sun. And even though the Bohr model is not reality, it is useful for a concept of the atom. So it's useful to calculate, say for example, we can calculate the radius of this circle, and we're actually going to do that in this video. So it's worth going into some of the details. But I should warn you that this is a lot of physics in this video as well, so if you don't like physics, you can jump to the next video where I show you the result of what we're going to calculate in this video. So going back to the electron here, let's say the electron is going around counterclockwise, and so the velocity of that electron at this point is tangent to the circle, so that's the direction of the velocity vector. So the electron has mass m, let's say, and the electron is going to feel a force, right? It's going to be attracted to the nucleus, right? So opposite charges attract, and so this negatively charged electron is going to feel a force towards the center of the circle. So that's a centripetal force, and in this case, we're talking about the electric force, right? So this is the electric force that's causing the electron to move in a circle. We can find the electric force by using Coulomb's law. So over here on the left, this is Coulomb's law. So the electric force is equal to K, which is a constant, times Q1, which is one of the charges. Let's just say that Q1 is the charge on the proton, times the other charge, Q2, which we'll say is the charge on the electron, divided by the distance between those two charges squared. So this is Coulomb's law. Let's go ahead and plug in what we know so far. So K is some constant, which we'll get to later. Q1, I said, was the charge on the proton, and the charge on the proton we'll say is E for now, so elemental charge. Q2, I said, was the charge on the electron, and the electron has the same magnitude of charge as the proton, but it's negative, so we put in a negative E here. All right, divided by the distance between the two charges squared. So force is equal to mass times acceleration using Newton's second law. So m is the mass of the electron, right? And this would be the centripetal acceleration since we're talking about a centripetal force. And we know that the centripetal acceleration is equal to v squared over r. So we can go ahead and plug in m times v squared over r. Immediately we can cancel out one of the r's. And since we only care about the magnitude of the force, right, we know the direction of the electric force. We don't really care about this negative sign, so we can just say we only care about the magnitude of the electric force here. So we can go ahead and simplify a little bit. This would be Ke squared over r on the left, and on the right, this would be mv squared. So continuing with some more classical physics, right, next we're going to talk about angular momentum, which is a tricky concept. So angular momentum is capital L. And the one equation for it is r cross p, where r is a vector and p is the linear momentum, right? So linear momentum is equal to the mass times the velocity. So we're talking about the linear momentum of the electron, so the mass of the electron times the velocity of the electron. And let's go ahead and plug this in for angular momentum. So we're going to take the angular momentum about the center of our circle here. So the angular momentum about the center, so r is a vector. Let me go ahead and draw r in. So r is a vector, right? It's the distance from the center to where our electron is. So we have r right there. This is the r vector, so I put in r. All right, this is a cross product. So this would be times the linear momentum, so times p, which is mv, times the sine of the angle between the two vectors. All right, so let's think about the other vector here. So the other vector is the momentum vector. So we took care of the r vector. The momentum vector is in the same direction as the velocity. All right, so if this is the direction of the velocity, that's also the direction of the linear momentum vector. And so the angle between those two vectors, right, the angle between those two vectors is obviously 90 degrees. So sine of 90 is 1. And so we can just say the angular momentum is equal to rmv times 1. So Niels Bohr thought that this angular momentum should be quantized. And so what he did was he set this angular momentum equal to some integer, so like 1, 2, or 3, or you could keep going, but let's just say an integer n times h, which is Planck's constant, divided by 2 pi. So this is what Bohr came up with, and he took this and he solved for the velocity. So let's go ahead and do that. So on the right, we're just going to solve for v. All right, so the velocity is equal to, this would just be n times h divided by 2 pi mr. So we just solve for v, and then we're going to take that, right? So we just solve for v, and we're going to plug that into our other equation over here on the left. And so let's go ahead and do that. We would have k e squared over r. On the right, we would have m times all of that, right? N times h over 2 pi mr, and then we'd square all of that. So let's go ahead and get some more room, and let's continue with our algebra here. So we'd have k e squared over r is equal to the mass times, so square everything in parentheses, so n squared h squared 4 pi squared m squared r squared. All right, we can cancel a few things. We can cancel out one of these m's here, and we can cancel out one of these r's. So now we would have on the left side k e squared is equal to n squared h squared over 4 pi squared, and we would have one m left and one r left. All right, so the goal of all this is to solve for the radius of that circle. And so to solve for r, we could start by multiplying both sides by 4 pi squared mr. So we would get k e squared 4 pi squared mr on the left side. On the right side, we would get n squared h squared. So we're going to solve for r. All right, so let's go ahead and do that. So r would be equal to n squared h squared over, all right, this would be over k e squared 4 pi squared m. All right, so now next we're going to take all of this stuff and we are going to plug in what those numbers are. So for example, h is Planck's constant, right? So we know what that is. That's 6.626 times 10 to the negative 34, and we're going to be squaring that number, and that's going to be over all of this. So k, right, if you've taken physics, you know that k is equal to 9 times 10 to the 9th. That's a constant. E is elemental charge, right? The magnitude of charge on a proton or an electron is 1.6 times 10 to the negative 19 coulombs. All right, so we put that in there, and that number needs to be squared as well. So we have a 4 pi squared in there. And remember, m was the mass of the electron. So you can look up the mass of an electron. It's 9.11 times 10 to the negative 31st kilograms. All right, and so that's a lot of math. And rather than take out the calculator and show you, you can do that yourself. And you'll see that that number comes out to be, this is equal to, I'll put it down here, 5.3 times 10 to the negative 11. And if you had time to do all the units, you would get meters for this. So go ahead and do that calculation yourself, and you would see that you get that number. That's a very important number. Let's plug that in, right, to what we have so far on the left. So the radius is equal to n squared times that number now. So 5.3 times 10 to the negative 11. And let's go ahead and plug in n is equal to 1, so an integer. So this represents a ground state electron in hydrogen. So if n is equal to 1, right, this would be R1 is equal to 1 squared times this number. And so obviously that's very simple math. We know that the radius, right, when n is equal to 1, the radius is equal to this number, 5.3 times 10 to the negative 11 meters. So let's go back up here. Let's go back up here to the picture so I can show you what we're talking about and why that's an important value. So this is what we just calculated. We calculated this radius, right, for a ground state electron in hydrogen. So we calculated this distance and we called it R1. All right, so the idea of Niels Bohr, right, by quantizing angular momentum, right, that's going to limit your radii, the different radii that you could have. So let's go ahead and generalize this equation. So we could say r, right, for any integer n would be equal to n squared times this number, times r1. So n squared times r1, which we just calculated to be 5.3 times 10 to the negative 11 meters. And so this is very important, right? So r for any integer n is equal to n squared times r1. And this means only certain radii are allowed because Niels Bohr quantized the angular momentum, right? So you have to have specific radii. And we'll talk about the other radii in the next video. So this video, after all that physics, we got this equation, and we're going to use that to go into more detail about the Bohr model radii.